Now we get to the most useful gas law, the ideal gas law. We can combine Boyle's law, Charles' law, and Avogadro's law all together and come up with one single law, and it's called the ideal gas law. The ideal gas law is this one right here. PV equals nRT. The pressure times the volume is equal to the moles of gas times a constant times the temperature. All the other gas laws talked about proportions, direct and indirect, and so they didn't have any constants in them. Here we've taken those and made it into a single state law, and it's got a constant. The ideal gas constant, R, is 0.0821 liters times atmospheres divided by moles times Kelvin. And that looks really messy in terms of units, but that's because of the units on all these other quantities. So the ideal gas constant, the constant means it's always the same. It's constant. So R is always this number. You may sometimes see it with different units, and then the number will change, but it's still the same value. This is the only one we're going to use in Chem 3A. So capital R in Chem 3A is always 0.0821 liter atmospheres per mole Kelvin. And I'll give that to you on an exam. So, important thing, each of the quantities has to be expressed in the units that are in R. So here it's liters, the volume has to be in liters, the pressure has to be in atmospheres, the amount of gas has to be in moles, and the temperature has to be in kelvins. Otherwise the units won't work out. So a lot of times in the problem, they'll give you volume in milliliters. They might give you pressure in millimeters of mercury or torr. You have to convert to the units that are in the ideal gas constant. You don't have to remember them. All you have to do is when you do this equation and you use R, you're like, oh, those are the units I have to have. I better make sure everything matches up with those units. This is an illustration of the relationships between the different gas laws. There's actually another one we didn't talk about, Gay-Lussac's law, relating pressure and temperature. But actually, all of these laws come out of the ideal gas law. So for those of you that are interested, I'm going to show you how you can derive all of these equations, whichever one you want, just using the ideal gas law, which some people remember it as, they say it's PIV-NERT, PV equals nRT, PIV-NERT. So PV is equal to nRT. So that's fine. And then we can also say, I'll put ones here. I'm not going to put a 1 on the R because R is always the same. And if I divide this by another ideal gas law, P2V2 equals N2 R T2. PV equals nRT. These two things in the denominator are equal. So if I divide this one by two things that are equal, then it's still an equality and it's fine. R doesn't change, so R cancels out. Name two variables that are in this. Just give me two. N and T? N and T. Okay, so we're going to derive the law that relates N and T. That's this one up here. No. Oh, fabulous. There isn't one. P and T? This one, VMP? Okay, we'll do this one. We'll derive Boyle's law. We're going to say that only the volume and the pressure are changing. We have constant N and T. That's what I was asking. I was asking for the constant ones. N and T. So the amount of gas is constant. If the amount of gas is constant, then N1 is equal to N2. So then those cancel out. If the temperature is constant, then T1 is equal to T2, and those cancel out. So what does all that equal to? 1. It's not equal to 0, it's equal to 1. Anything divided by itself is 1. So there I've got P1V1 over P2V2 equals 1. Well, if I multiply both sides by P2V2, then these P2's cancel, the V2's cancel. And what am I left with? P1V1 equals P2V2. Boyle's law. So I sort of accidentally remember some of these equations because I say them and teach them so often. But if I need a gas law, I'm going to do this. I always remember PV equals nRT. And I'm just going to go one over the other, and then I'm going to cross out anything that doesn't change, and then I'm just going to rearrange that for the thing I need to find. Works every time. So if you like that, awesome. If not, I'll give you the equations on the test. Let's do an ideal gas law problem. Calculate the volume occupied by 0.845 moles of nitrogen gas at a pressure of 1.37 atmospheres and a temperature of 315 Kelvin. One of the tricky things about gas law problems is on a test, they're not going to have the label up here that tells you which gas law it's about, right? So the table idea always works. Make a table, write in the information. What we're going to find with this one is that we really didn't need the table, but it's okay. It's still fine. We go 1 and 2 just like we did before. 0.845 moles, we'll write that down, 0.845 moles. Oh, I'm writing much smaller suddenly. You guys read that okay? And then the next number is 1.37 atmospheres. And then we've got the next number, 315 Kelvin. And then let's identify these. Volume, calculate the volume. This many moles of gas. What's the variable for that? N. And this is the pressure, right? So that's going to be P. And this is temperature. We got all the numbers out, and there's nothing in row 2. Well, let's just get rid of row 2 then. Apparently we didn't need it. Is that going to cause us a ginormous problem? No. Look what we did. We labeled the numbers. If you only have one row of numbers, you're going to need the ideal gas law, PV equals nRT. PV equals nRT. What is the question asking me to find? The volume. Calculate the volume. Okay, well, here's PV equals nRT. Let's rearrange this for volume. So we'll divide by P on both sides. These P's cancel out. So volume equals nRT divided by P. So I've got N labeled there, 0.845 moles. Oh, this is just, I'm going to start again at the bottom. I'm having zooming issues. V equals nRT over P. N is 0.845 moles. What's R? We don't have R. It's the gas constant. If you don't have it memorized, look it up. 0.0821. And then those funky units. Liter, atmospheres, per mole, Kelvin. Are these the units that are being used in our numbers here? Yeah, they are. So we're okay. We don't have to do any unit conversions. 0.0821 liter atmospheres per mole Kelvin. And the temperature, wasn't that kind? They gave us the temperature in Kelvin. They don't do that very often. Divided by the pressure, 1.37 atmospheres. Now check out the units. Moles cancel moles, Kelvin cancels Kelvin, atmospheres cancels atmospheres. The unit that's left is liters, which is a unit of volume. 0.845 times 0.0821 times 315 divided by 1.37. This should have three significant figures. 15.95 rounds up to 16.0. The unit is liters. That's the volume of the gas. Any questions? Let's do another one. An 8.5 liter tire is filled with 0.55 moles of gas at a temperature of 306 Kelvin. What's the pressure of the gas in the tire? I'm going to approach this one a little bit different. I'm just going to write down the numbers and label them. You can make the table. That's absolutely fine. 8.5 liters. Well, liter is a unit of volume. That must be the volume. 0.55 moles of gas. That's the unit for N. And the temperature is 306 Kelvin. That's the temperature. What is the pressure? Pressure equals question mark. And then just for good measure, let's write down R. 0.0821 liters times atmospheres divided by moles times Kelvin. I don't have anything changing. It's just a tire just sitting there. And we want to know what the pressure is. Ideal gas law, PV equals nRT. So this time I'm going to solve for P. The pressure is the nRT over V. So 0.55 moles times the constant, 0.0821 liters atmospheres per mole Kelvin, and the temperature 306 Kelvin divided by it really doesn't want to draw a line there. There we go. The volume 8.5 liters. Do the units match up? Do they cancel out? They do. I've got moles and moles. I've got liters and liters. If I had liters and milliliters or liters and gallons, I would have a problem. But they're matching up. And Kelvin, as opposed to Kelvin and Hobbes, I suppose. Pressure equals 0.55 times 0.0821 times 306 divided by 8.5. Looks like this one needs two significant figures, so 1.6 atmospheres. Any questions? There's like an endless number of problems that could be asked about gas laws. It comes down to giving you a bunch of variables and leaving one for you to solve for. You identify the variables, you choose the correct equation, you rearrange and solve. This is Skill Builder 11.7. See the title, The Ideal Gas Law Requiring Unit Conversion. Okay, so this is a more typical sort of problem. The units are not going to be set up all perfect for us. How much volume does 0.556 mole of gas occupy when its pressure is 715 millimeters of mercury and its temperature is 58 Celsius? You can still do the table. I'm going to do just labeling. So N is 0.556 moles. I know that's N because of the unit. It says the pressure is 715 millimeters of mercury. The temperature is 58 degrees Celsius. Well, I know that's not good. Let's convert that right away. Plus 273, 58 plus 273, 331 Kelvin. All the gas law problems have to be temperatures in Kelvin. And they're asking us to find the volume. And then let's write down what R is, because we're going to need that. The units on R tell us what units N, P, T, and V are going to have. Is this an okay unit for N, moles? Yeah, perfect. How about pressure, millimeters of mercury? No, we need atmospheres. So we need to convert it. It's best to convert it before you stick it into the equation. So I need atmospheres on top. And I need millimeters of mercury on the bottom. This is one we use a lot, so it's a good one to memorize. 1 atmosphere is 760 millimeters of mercury. Now, you don't want to flip the numbers backwards and say that 760 atmospheres is 1 millimeter of mercury. Think about the barometer. The barometer actually, is a reasonable sized column of mercury. It's not a little tiny bit for this huge, ginormous pressure. So 715 divided by 760, that's going to be 0.940. There's my third sig fig. I'm going to add 2 more atmospheres. Best not to round until you get to the final answer. I already converted temperature. Kelvin is a good unit for the ideal gas law. So now I'm going to get out PivNert. I'll just throw them up in the middle here. PV equals nRT. Solving for volume again. Divided by pressure. Divided by pressure. So volume is nRT over P. 0.556 moles. Yeah, 0.0821 liter atmospheres per mole Kelvin. Temperature 331 Kelvin. Pressure 0.940 94079 atmospheres. 0.556 times 0.0821 times 331 divided by 0.94079. I look at all the numbers, and it looks like I should have 3 significant figures. This one's 3, this one's 3, this one's exact. When I add these, I still have uncertainty in the ones place, so that has 3, and this has 3. So this is going to be equal to 16.1 liters. Any questions? We can use the ideal gas law, if we know the mass of the gas, to calculate its molar mass. So let's see how we would do that. A sample of gas has a mass of 38.8 milligrams. Here's its volume, its temperature, and its pressure. Find the molar mass. What is molar mass? The mass of 1 mole, right? The molar mass is how many grams per mole. So molar mass equals moles divided by grams. Do we know the mass of this sample?
Yes.
We do. Here we have it in milligrams. Come on, pointer, milligrams. Well, could we convert that to grams? 38.8 milligrams. Milligrams on the bottom, grams on top. Milli means 1 times 10 to the minus third. And so this is equal to 0.0388 grams. So the molar mass equals some number of moles divided by 0.0388 grams. Could we find out how many moles of gas there are? We could use the ideal gas law. PV equals nRT. We want to get N by itself. Divide by RT. Those R's cancel, T's cancel. So N is equal to the pressure times the volume divided by the gas constant times the temperature. They gave us the volume, they gave us the temperature, they gave us the pressure. And the units on all of them are not quite right. Nice. We can do this. So volume is 224 milliliters. It has to be in liters. So we convert. Milliliters on the bottom, 1 times 10 to the minus 3 liters on top, 0.224 liters. The pressure they gave us in torr, we need it in what? Atmospheres. So we multiply by atmosphere, we divide by torr. 1 atmosphere is 760 torr. .1658 atmospheres. And then there's that temperature. Where am I going to sneak that in? Over here. Temperature is 55 degrees Celsius. So we're going to add 273. And that is equal to 328 Kelvin. Now we can put these numbers into this equation. The pressure, 1.1658 atmospheres. And the volume, 0.224 liters. R is always the same, 0.0821 liters, atmospheres per mole, Kelvin. And then the Kelvin temperature is 328 Kelvin. We got 2 numbers in the denominator. Be careful. 1.1658 times 0.224 divided by 0.0821 divided by 328. 0.00969, yeah, 3 sig figs again, 74 moles. That's the number of moles of gas in this sample. But we're trying to find the molar mass. And so that's that missing piece that we need right up here, the number of moles. 0.0096974 moles. I'm underlining the last significant figure so that I can keep track of it without going back over the whole problem. So I take that number and I divide by 0.0388. And I don't know what I did, but that's not right. 0.00. I know what I did. Do you see what I did? Duh. Molar mass isn't moles per gram. It's grams per mole. What? I don't know. See, I left my rock star in the car, and my head is starting to pound. I don't have a problem. I could quit anytime. I just don't want to. Okay, grams per mole. We'll just blame it on lack of caffeine. Okay, so we figured out the grams earlier. And we're going to divide by the number of moles. This is looking better. Except for that. 96974 moles. Units are your friends, though. 0.0388 divided by 0.0096974 equals, and this should have 3 sig figs, so 4.00 grams per mole. What really tipped me off that I had it upside down earlier is I came up with like 0.024 moles. And I'm like, now wait a minute. Hydrogen is the smallest atom. Atoms of hydrogen have a molar mass of 1 gram per mole. There are no substances that have molar masses less than 1, right? There just aren't. This molar mass is very distinctive. This is obviously helium. Helium has a mass of 4 grams per mole. There's not a lot of possibilities when you're down among these little guys. Any questions? That one is just like the one we did. I'm going to skip it. Gas behavior depends on conditions. You might be wondering, why is that ideal gas law called the ideal gas law? Well, that's because it works when gases behave like they're supposed to, like ideal gases, but they don't always. These are the conditions under which gases obey that law. Relatively high temperatures and relatively low pressures. Because under these conditions, the particle size is very small relative to the amount of empty space between. These particles, being at a relatively high temperature, are moving fast enough that when they collide with each other, they don't interact. Under non-ideal conditions, low temperature and high pressure, where we're squeezing a gas and cooling it down, now the particles are getting closer and closer together, so we can't necessarily say that the volume of the gas itself is negligible compared to the space it occupies. And when these are moving slower, they will begin to stick to each other and interact with each other. So under these sorts of conditions, the ideal gas law doesn't quite work. I'm just telling you about it, and we're not going to do anything else with it.